Hey folks, today we're going to discuss 2.4, which is just more shortcut rules for derivatives. We took shortcut rules for derivatives in 2.3 on polynomials and rational functions, which are quotients of polynomials. Today we look at shortcut rules for derivatives of trigonometric functions. The derivative of sine of x is cosine of x. ddx of sine x equals cosine of x. Second rule, ddx of cosine of x is negative sine of x. And ddx of tangent of x is secant squared x. Just go ahead and memorize them. Let's see if we can believe in our heads that the derivative of sine of x is cosine of x. We'll start by graphing 2 periods of sine of x. Now we go ahead and graph its derivative. We're going to do it graphically, right? We're starting with sine of x. We want to come up with cosine of x graphically. So how might we do this? Do you remember this? The slopes of f are the dependent values of f prime. So where does the slope of this sine function equal 0? Where's the slope of sine equal 0? It seems to have a slope of 0 right here, right here, right here, and right here. What are those independent values again? Pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2. So what are we saying? We're saying that the derivative function should have zeros at those locations. So let's go ahead and put them in. We'll put them in black. Next, we ask ourselves, where is the slope of the sine function positive? Well, I think you can see that from negative 2 pi to negative 3 pi over 2, what would you say about the slope of the original sine function? It's positive, which means you have to have what kind of values for the derivative? Positive values. Show me positive values. Yeah, above the x-axis. So maybe something that looks like this. These are all positive for sure. All right, now look at this next chunk here. From negative 3 pi over 2 all the way to negative pi over 2. What do you notice about the slopes of the sine function? They're all what? Negative. Therefore, the dependent values of the derivative must be what? Negative. Show me negative. That's right, below the x-axis. The only way I'm going to go from this 0 right here to this 0 right here with only negative is something that looks like this. So we continue the process. We look from negative pi over 2 all the way to pi over 2. The slopes of sine are positive. Therefore, the dependent values of its derivative must be positive. The only way you're going to get that is to connect the two zeros and keep your dependent values positive. And then the process keeps going and going. Now just take a look at that black function. What do you notice about it? What is it? It's cosine of x. It's y prime equals cosine of x. And the original function was y equals sine of x. You can just look at it and see that. Therefore, what we established graphically is that the derivative of sine of x is cosine of x. We established this first rule graphically. We could also establish this rule graphically, going back to our limit definition of the derivative. Let's do that at least once. So we want to find out the derivative of sine of x. Using the limit definition of derivatives, take the limit as h approaches 0 of what? Sine of x plus h minus sine of x over h. Now we can rewrite this indeterminate form by expanding sine of x plus h. Do you remember how to do this? That's pre-calculus formula, sine of x, cosine of h, plus cosine of x, sine of h. Okay, that minus sine of x over h. You have to use that pre-calculus formula we learned. From there, we're going to take a couple moves that maybe are not entirely obvious. We're going to break up this indeterminate form, this fraction here, into two smaller fractions. So we're going to take sine of x cosine of h minus sine of x over h, and the rest of it, which is plus cosine of x sine of h over h. And then we're going to factor out from the first term sine of x and from the second term cosine of x. The reason we did that is then we'll be actually able to be solving these limits. We begin by just writing out this limit and all its component parts using limit laws. So we got the limit as h approaches 0 sine of x times the limit as h approaches 0 of cosine of h minus 1 over h, plus the limit as h approaches 0 of cosine of x times the limit as h approaches 0 of sine of h over h. Now some of this is going to be obvious in the plug and chug phase, some of it is not. The limit as h approaches 0 of sine of x, it means plug 0 into the in for h. Well, there's no h there, so that's just sine of x. How about the limit as h approaches 0 of cosine of h minus 1 over h? Well, that one you may know or you may not know. You're supposed to be familiar with it enough in the textbook that you know that that equals 0. All right. Then, what's the limit as h approaches 0 of cosine of x? Well, no matter what h is approaching, cosine of x is just cosine of x. And now, you're supposed to take the limit as h approaches 0 sine of h over h. We've seen that function. That's the function that's kind of moving from left to right almost on the x-axis. Then it slides up to 1, but has a hole in it and comes sliding back down to the x-axis. Remember that function? We've seen it a couple times. And what was the limit on that one? As h approaches 0, it was 1. Hopefully you remember that. All right, so what are you left with? You're left with cosine of x. So what we've established algebraically here using the limit definition of derivative is that the derivative of sine of x is in fact cosine of x. Again, that first rule. There are 3 more rules for you to memorize here. Rule 4, the derivative of cosecant of x is negative cosecant x cotangent of x. The derivative of secant of x is secant x tan x. And the derivative of cotangent of x is negative cosecant squared of x. Memorize these 6 rules in addition to the rules for polynomials and rational functions from 2.3. Now all that's left is to use these rules in some problems. First, an object at the end of a vertical spring is stretched 4 centimeters beyond its rest position and released at time t equals 0. Its position is given by s, which equals f of t, which equals 4 cosine of t. Find the velocity and acceleration functions. All right, so we write the position function. The position function, s, goes by f of t equals 4 cosine of t. How am I going to get the velocity function, v of t? Well, that's just f prime of t. Use a shortcut rule now. Well, what's the shortcut rule again for cosine of t? Derivative of cosine of t is negative sine of t. So what's the derivative here? Negative 4 sine of t. Okay, now we're going to find acceleration, which is f double prime of t. Take a derivative again. What's the derivative of sine of t? Cosine of t. So we got negative 4 cosine of t. What are some observations you can immediately make about the position function right here? Well, what's the amplitude of this position function? 4, right? Which means the position of the particle is going to vary over time between what 2 values? Negative 4 and 4, because there's an amplitude of 4. Then we look at the velocity function. What can you tell me about this velocity function? What are the dependent values that it can vary over? Well, sine of t can only be from negative 1 to 1. So the output here, the velocities could range anywhere from what? Negative 4 to 4, right? So that means that my velocity is very strongly in the negative direction at negative 4, and my velocity is very strongly in the positive direction when it's at 4, and it could be anywhere in between that. So my greatest speeds here are 4. Finally, the dependent values of acceleration. The accelerations vary from negative 4 to 4. Here's a second problem then. Find the 27th derivative of cosine of x. Well, that sounds like you have to do a lot of work. Until you start working with derivatives of cosine of x, and then you see what happens. Here's the trick. If y equals cosine of x, then y prime equals negative sine of x. Therefore, y double prime of x equals what? Negative cosine of x. And y triple prime? sine of x, and y quadruple prime, which remember you put in that parentheses like that, is equal to cosine of x. Now, what do you notice here? The original function and its fourth derivative are the same function. So the cycle is going to repeat right after that, right? What if I went to y fifth of x? I'm going to get negative sine of x. Sixth derivative, negative cosine of x. Seventh derivative, sine of x. And then what do you see again when you hit the eighth derivative? You're back to cosine of x again. See this repeating process? You're not surprised by this. I don't think. So what would you suspect? You just drop down to the y 27th derivative. You would get, let me give you a second to think about that. You'd get sine of x. The return to cosine of x seems to happen on the 4s. So on y 24th, you'd be back to cosine of x, which means at y 27, you'd be at sine of x. So we take a third example. Here, f of x equals secant x over 1 plus tangent of x. We're asked to find the derivative f prime of x, and then find the values of x for which f has horizontal tangent lines. Well, what type of function is f? It's a quotient function. No, it is not a rational function. It's not a quotient of polynomials. It's a quotient of trigonometric functions. So this thing here is considered just a quotient function. And how do we take its derivative? You got to use the quotient rule. Remember the quotient rule? Low d high minus high d low over low low. Say that with me. Low d high minus high d low over low low. All right, here we go. Low means the bottom function. 1 plus tangent of x. D high means the derivative of the numerator. What was the derivative of secant of x? Secant x tangent of x, this shortcut rule from today, minus low d high minus high, that's the top function, secant of x, times the low, d low, derivative of the bottom. What's the derivative of 1 plus tangent of x? Well, derivative of 1, 0. What's the derivative of tangent of x? Secant squared x. All over low, low, which is just the bottom function squared. So that's f prime of x. We can certainly clean this up just a bit, can't we? We can factor out secant of x in the numerator, leaving us with tangent of x plus tangent squared x plus secant squared of x, all over 1 plus tangent of x squared. Then we can use the Pythagorean identity, secant of x times tangent of x. What is tangent squared x plus secant squared x? Minus 1. All over 1 plus tangent of x squared. So how will I know when the function f has horizontal tangent lines? Well, when f prime of x equals what? 0, since f prime of x is the slope of f. So we basically want to set f prime of x equal to 0. We want to find the zeros of this derivative function. We want to find its zeros. So I'm going to set f prime of x equal to 0, which means I'm essentially saying that what? The numerator has to equal 0. All right, so either when secant of x equals 0 or when tangent of x minus 1 equals 0. Well, secant of x, this thing is never going to equal 0, right? That's not a thing. If you remember what the shape of secant of x. Tangent of x minus 1 equals 0. This tells us that x will equal k pi plus pi over 4, where k is an element of the integers. You remember doing this in pre-calculus work, in our trig work. How can you see this? Well, you know that tangent of pi over 4 is what equals 1. 1 minus 1 equals 0. And then how often will this repeat? Every pi. Why? Because the fundamental period of a tangent function is pi. Well, that's the main content for this section. There's more derivative rules and how you might apply them. A few other things that they do in this section is just work on limits, just basically that portion of the limit of a difference quotient that we call limits. And they work on it so that if you ever do want to be able to derive one of these shortcut rules in the future, I don't know why you would, you have those resources under your belt, right? So we've already seen things like this. The limit as theta approaches 0 of cosine of theta minus 1 over theta equals 0. And the limit as theta approaches 0 of sine of theta over theta equals 1. And we use those in the derivation of cosine of x from sine of x, as you recall. Well, there's kind of other limits here that show up in these justifications if you want to do the algebraic justification. So they want you to practice those limits. And so they have you solve this limit. The limit as x approaches 0 of sine of 7x over 4x. Of course, you just plugged in 0 here, you'd have an indeterminate form, so you'd have to do some more algebra. What is it? So we have a 7/4 offset by the elimination of the 4 and the 7. In other words, we've drawn out 7/4, leaving us with sine of 7x over 7x. And that's no different than what's right above it, which is the limit as theta approaches 0, sine of theta over theta equals 1. So, 7x is essentially theta. So you're left with just a limit equal to 7/4. And here's a final limit. The limit as it approaches 0 of x cotangent of x. How could we rewrite this? We could write this as the limit as x approaches 0 of x cosine of x over sine of x, which can be broken apart into the limit as x approaches 0 of cosine of x over the limit as x approaches 0 of sine of x over x. Well, plug and chug, now you know the cosine of 0 is 1, and we know that the limit as x approaches 0 of sine of x over x is also equal to 1, so this limit is 1. Again, you're like, why are we all of a sudden doing limits of trigonometric functions? So we kind of go back in time. Yes, a little bit. This is just if you ever wanted to flush out those shortcut rules, prove those shortcut rules using limit definitions of derivative. These are the kind of limit algebra you'd encounter. All right, have a good one, folks.